Gigantic black holes existed a cosmic eye blink after the Big Bang. That should be impossible. Well, the James Webb Space Telescope has either made the problem much worse or solved it. Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So for those of you who do support, thank you so much. But don't get me wrong, there are perks and they're good. There's a link in the description if you'd like to join. This really would be a huge help. Next up is our newest merch. Every great space saga starts somewhere. Ours started 13.8 billion years ago. So celebrate one of the most inspiring universes ever created by celebrating the space-time which contains them all. Links to the merch store in the description. Black holes can grow fast, exponentially fast. The more mass they consume, the stronger their pull and the faster they can eat. The largest supermassive black holes seen in the late universe can be several billion suns in mass, but they've also had several billion years to grow, typically during brief periods as bright quasars when they feed on the incandescent whirlpools of infalling gas. But then we started to find such enormous black holes at earlier and earlier times, in quasars shining out of the first billion years or less of cosmic time. Now, even exponential growth doesn't seem fast enough to explain how these monsters formed. The James Webb Space Telescope only made things worse, finding faint specks of reddened light, dubbed little red dots, that seem to be powered by outsized black holes in the first several hundred million years of cosmic history. What's going on here? Is the early universe forming gigantic black holes in ways we haven't imagined? Do we completely not understand how black holes grow? Is the universe older than we thought? Well, recently JWST found a very unusual little red dot that may solve everything. We assume that supermassive black holes grow from the much smaller black holes left behind when massive stars die, stellar black holes. The first generation of stars were probably especially enormous and so left behind especially large seed black holes, let's say 100 times the mass of the Sun compared to the 5 to 15 solar masses in the modern universe. At the theoretical maximum accretion rate, black holes double in size roughly every 33 million years, so that 100 solar mass black hole is going to take at least 700 million years to give us a billion solar mass supermassive black hole. But we see these gigantic monsters and even larger from within the first 700 million years, so it sounds like it's just barely possible to go from stellar to supermassive in that time? Well, not even. The first stars took at least 100 million years to form after the Big Bang, probably more, and it's hard to come up with scenarios in which a black hole feeds without any interruption for so long. Something needs to give. There are two obvious possible solutions to the problem of overly massive early supermassive black holes. One, black hole seeds were much larger than expected, or two, black holes grew much faster than we thought possible, so started bigger and/or grew faster. There are various ways to start big, like having ridiculously gargantuan stars in the very early universe, or even collapsing clouds of pristine hydrogen directly into black holes without going through a stellar stage. Now, growing faster requires creative ways to get around the theoretical feeding limit that I mentioned, and which we will come back to. But when the first overly massive black holes were discovered at around the turn of the millennium, some moderate rethinking of black hole formation and growth seemed enough to explain the issue. But as our telescopes got better and we saw two big black holes at greater and greater distances, our re-theorizing had to do a lot more work to explain them. And then came JWST and the little red dots, and things got much worse. Little red dots are tiny compact objects that appear extremely red in JWST images of the distant universe. And many of them have broad emission lines, especially from hydrogen. Now, emission lines are unusually sharp spikes that occur at very specific wavelengths due to electron transitions in specific atoms. These lines can be broadened if the gas producing the line is moving very fast due to the Doppler effect. These broad emission lines are classic features of quasars where the gas is moving at enormous speeds, either orbiting or flowing towards or away from the black hole. These features are a standard way to measure the mass of a distant supermassive black hole. If we assume that the gas is moving fast because it's in orbit around that black hole, then the width of the line gives the orbital speed and hence the black hole mass, some assumptions included, and I'll come back to those. Based on the line widths in the little red dots, black hole masses from millions to hundreds of millions of suns have been measured. Now, those aren't quite the billions of suns like the biggest supermassive black hole seen in the early universe, but they're definitely in the supermassive category. And these black holes are also way too big for the galaxies that they live in. Supermassive black holes are always found in the centers of galaxies, and in the modern universe they appear to have grown in relative lockstep with their galaxies over the age of the universe. Bigger galaxies have bigger central black holes. But the host galaxies of those little red dots are tiny compared to their black holes. That suggests that the central black hole massively outpaced its galaxy as it grew, or started out ridiculously large. So far, JWST and its little red dots are just making this problem worse. Then along comes MOM-BH1 star. It was first detected by JWST in the Primus survey in 2023 and identified as weird and followed up by Rosenthal and collaborators. They presented the results of their spectroscopy and their interpretation in Nature very recently. This particular little red dot existed a mere 660 million years after the Big Bang. It has a spectrum that on one hand looks like a classic little red dot with broad emission lines that suggest hydrogen gas moving at more than 3,000 kilometers per second. That screams accreting black hole. On the other hand, it also kind of looks like a star. It has what we call a Bahar break, a huge chunk missing from its spectrum due to absorption by hydrogen. In emission lines, like in broad lines seen in quasars, an energized cloud of gas emits specific wavelengths of light as electrons in its atoms drop down in energy levels. But if a gas cloud happens to obscure another source of light, those same specific wavelengths can also be sucked out of that background light as electrons in the gas absorb photons to jump up in atomic energy levels. That happens with stars. The stellar atmosphere absorbs specific wavelengths of light coming from deeper in the star. Because it's only the light that's able to excite an electron that gets absorbed, this leads to a spectrum with many narrow gaps. Sufficiently energetic photons can completely free an electron from its atom. So, in the right conditions, all photons above this so-called ionization energy get absorbed by the gas, and that translates to the absorption of all photons below a specific wavelength corresponding to that energy. The Bahar limit is the wavelength below which all photons get absorbed by hydrogen gas, 364.6 nanometers. More precisely, it's the absorption limit for hydrogen with electroncity in the second energy level. But for many stars, their outer atmosphere is full of hydrogen in this state, and so all light from deeper in the star that's beyond the Bahar limit gets sucked up in the atmosphere and doesn't escape. The result is a spectrum like this. We call this 364.6 nanometer transition the Bahar break. Right, good. So, this is the spectrum of MOM-BH1 star. It has a very clear Bahar break. It looks like a star, but actually with a stronger Bahar break than most stars. It also looks like a quasar with its broad emission lines. So what's going on? Well, it could be that this Bahar break is really from the galaxy surrounding the quasar. After all, galaxies are made of stars and stars can have Bahar breaks, but there are other hydrogen absorption lines in the spectrum that suggest that we're looking through an enormous depth of hydrogen at colossal densities, something the size of a solar system with a density of between 1 billion and 100 billion atoms per cubic centimeter. That is not what stars look like. It's not even what many stars added together look like. The thing looks like a single giant atmosphere surrounding something, presumably the black hole. This type of object, a star-like envelope powered by an accreting black hole, has been dubbed the black hole star. Not sure if the name will stick, but it's catchier than little red dot. We're used to seeing accreting blacking holes that look more like this, a black hole surrounded by a relatively thin whirlpool and accretion disk of stuff that's pouring in to feed the black hole. Most of the light we see comes from the inner part of the disk, where its infall results in crazy speeds, and friction between adjacent streams heats the disk to an incandescent glow. Most of that light has a relatively free path away from the disk, and so we only see strong absorption in rare cases, and never this sort of complete cocooning of the inner light source. Okay, so apparently quasars can look very weird in the early universe, but that weirdness may actually answer a lot of our original questions. This cocoon changes what light can get out, but it also changes what matter can get in. Now, earlier I mentioned a theoretical limit to how fast black holes can grow. As stuff falls into a black hole, it heats up and radiates, but that same radiation pushes back on the infalling material and can slow and even stop accretion. In the most obvious scenario, the infalling stuff is ionized hydrogen and the outgoing radiation is scattering off its electrons. In that case, there's a very clean limit for how brightly black holes can radiate and how fast they can grow. It's called the Eddington limit. The vast majority of accreting black holes we've measured are below this limit. It takes some creative tweaking of the accretion physics to get much above this limit. A lot of the work in understanding how early black holes could have gotten so big is about finding new ways to break the Eddington limit, of enabling what we call super Eddington accretion. Well, our new little red dot has given us solid evidence that the Eddington limit has been thoroughly shattered. One of the assumptions in determining the Eddington limit is that the radiation eventually escapes the object. It can take a long time for any one photon to fight its way through the surrounding gas, but as long as it does ultimately escape, then it's done the maximum work in pushing that gas outwards. But what if some of the light never escapes? In the case of an extremely dense infalling cocoon, the amount of time taken for a photon to escape can exceed the amount of time it takes the gas to reach the black hole. That means photons get swept down and swallowed by the black hole before they can exert maximum outward push. This is a recipe for super Eddington accretion. Astrophysicists have speculated on this sort of process for the extreme growth rates of early black holes, but MOM-BH1 star may be the most direct evidence we've discovered. But this doesn't quite solve our problem, because our estimate of the black hole mass in this object is still relatively huge, certainly for such a small galaxy. If this and all of the other little red dot black holes are so big, when did they get this big? There should also be a population of smaller black holes with crazy accretion rates. But in fact, this one object may solve that problem too. As I said earlier, black hole masses for distant quasars are typically measured from the breadth of their emission lines, because these indicate orbital velocities around black holes. But what if the emission line breadth is not due to orbital motion? In the case of such a densely cocooned source, photons trying to escape bounce many times on their way out. That scattering blurs and broadens the usually sharp spike of an emission line. The authors of this study explored how much broader a broad emission line might become in this sort of scenario. They figure that the velocity could be overestimated by a factor of 5. So a 600 km per second orbital velocity gets blurred out so it looks like 3,000 kilometers per second. And the inferred black hole mass goes up as velocity squared, so a million solar mass black hole can look like a 25 million solar mass monster. Now, a million suns worth of black hole is still technically supermassive, but it's borderline. It's much more reasonable for such an early cosmic age and such a small host galaxy. They are black holes that, at the rate of super Eddington accretion that we might also be seeing, can sensibly give us the colossal early supermassive black holes that have been vexing us for decades now. I should also add that this interpretation of the data is just that, an interpretation. We'll need more observations and to find more objects just like this to corroborate the story of the black hole star as part of the answer to the problem of gigantic early black holes. But it is a step further in understanding the strange state at the beginning of spacetime.